Hello, my name is Roger Watson, and this presentation is about making questionnaires better with item response theory. Specifically, it's about Mokken scaling. First, let's take a look at measurement in social research. Measurement in social research uses surveys and questionnaires, and we look at the properties of these questionnaires using psychometrics. And amongst the psychometrics that are available to us are the reliability and the validity of those questionnaires. Item response theory lies somewhere in between both reliability and validity. The purpose of measurement in social research is to investigate latent variables or latent groupings, and there are a range of methods for doing this. Most commonly, classical test theory, which includes methods like factor analysis and reliability measures like Cronbach's alpha. We'll come back to factor analysis later in the session and compare it with item response theory, and of course item response theory, which is the subject of this session. And there's also latent class analysis, which looks at groups of people rather than groups of variables. So classical test theory includes factor analysis and internal consistency. There are some problems with classical test theory, despite its usefulness and its wide application. One of the problems is that any combination of scores on any set of items can give the same score on the latent trait. Therefore, you don't know what a score actually means, and I'm going to demonstrate this towards the end of the session. Item response theory includes methods like rash analysis, partial credit model, and Mokken scaling. Mokken scaling is a non-parametric method of item response theory. Again, we'll pick this up later. The advantages of item response theory, whatever method you're using, is that only a specific set of items produces a given score on the latent variable. Therefore, you know how to interpret that score because you know what it means. The unit of analysis in item response theory is the item characteristic curve, which looks something like this. This particular one is demonstrating the relationship between personability and the expected value, but just keep the shape of the item characteristic curve in mind, and also that they're also known as item response curves and item response functions. They go by various names. Mokken scaling adheres to the assumptions of item response theory. I'll explain what those are very shortly. It's a stochastic version of Guttman scaling. Again, I'll explain what that means. And it produces hierarchical and cumulative scales. The assumptions of item response theory are that sets of items are unidimensional, in other words, that they're all measuring the same latent trait. Another assumption is that items are locally stochastically independent, in other words, the score on one item does not depend on the score on another item. Instead, it depends on the relationship to the latent trait. Item characteristic curves should be monotonely homogeneous, and I'll demonstrate that in some subsequent slides. They should also, for dichotomous items, for example yes-no items, show double monotonicity. And for polytomous items, they can show invariant item ordering. It's not an essential feature of a Mokken scale, but it's a very useful feature. Again, we'll define these in subsequent slides. So let's look at the concept of a cumulative scale. In a cumulative scale, items are ordered reproducibly. In other words, every time you run those items through an analysis from whatever group, they should, in theory, be reproducible in the order in which they appear. The items are ordered meaningfully. There's no point in ordering items according to an item response theory and it doesn't mean anything, so they have to mean something. And the score on an item indicates the extent to which the latent trait is present. In other words, the score on an item is related to the latent trait. And the sum of item scores is a measure for the order of the latent trait. In other words, if you add up the items, you know how far along the latent trait an individual who's responded to those items is. So let's look at an example of a cumulative scale. These are also known as implicational scales, because the score on one item implies something about the score on the other items. So this is quite facetious, but it makes the point, I think. Here we have a set of items about how much people like Scottish people. I'm Scottish, so I'm using myself as an example. So one item is I would not object to sitting next to a Scottish person on a bus. The next item is I would not object to having a Scottish family live next door. Next item is I would have no objections to having a Scottish person dine in my house. 4. At a party I would not hesitate to dance with a Scottish person. And 5. I would have no objections to my son or daughter marrying a Scottish person. I think you can see that there's a very clear hierarchy in those items there. Many people would not object to sitting next to someone that they didn't especially like on a bus, but they might have strong objections to them marrying their son or daughter. So if these were cumulative yes-no items, and yes was 1 and no was 0, the maximum score on the questionnaire would be 5. So if somebody scored 5, you would know that they had scored yes to all of those items. In other words, they would have objections to they would have no objections to their son or daughter marrying a Scottish person, and by implication they would have scored yes to all the other items. However, somebody who scored 1 would score only on I would not object to sitting next to a Scottish person on a bus, but wouldn't score on any of the other items. Therefore, the person with the lower score would be more prejudiced against Scottish people than somebody who scored 5. And the direction in which this travels is from the bottom to the top in terms of what we call difficulty. The items that are more unusual to score, or literally more difficult to score, or less easily adopted by people, are described as being more difficult. That term difficulty is specific to item response theory. One of the earliest forms of item response theory was Guttman scaling, and Mokken scales are derived from Guttman scales. And this is Louis Guttman, who lived from 1916 to 1987, who developed Guttman scaling. We're not going to go into Guttman scaling in any great detail. This is an example of how a set of responses to a Guttman scale might look. You see that there are various respondents and various items and various possible responses for yes or no. And you can see that there's a rough pattern developing there. The person who's numbered 33 doesn't respond to the items at all, whereas the person who's numbered 7 responds positively to all of them. And there's a slight evidence of a hierarchy in between. However, there are people who are exceptions. None of these methods are perfect. Another example of a Guttman scale is this photograph I took at my car wash. So if you imagine the different classes of wash, from tyre dressing up to soft brush, wash and dry, or the items and the scores or the prices, you can see that of course it gets more expensive the more you want, and that forms a hierarchy of items according to the prices. Of course there are some exceptions there are some gaps. As I say, none of these things are perfect. I've already made the point about the item characteristic curve being the basic unit of analysis in Mokken scaling. This is what the item characteristic curve, or the item characteristic relationship, looks like in Guttman scaling. It's traditional along the x-axis to represent the latent trait as theta, and the y-axis as the probability of scoring on that latent trait. So here are two items, I and j, from a Guttman scale, and you'll notice that there's not a curve. These are yes or no items. Guttman scaling is described as being deterministic. People either have the score or they don't have the score, and it's not very tolerant of error. And this doesn't really happen in the real world. when people score on items, they have tendencies to score on them. They have more or less probability of scoring on them. And that's why Mokken scaling, which is a development of Guttman scaling, is described as being stochastic. It's dependent on the probability of someone responding to an item. So items and traits are related by what's called a dominance model in Guttman scaling. You either score or you don't, and one item has to be positioned in a particular place on the latent trait, and only on that place on the latent trait. However, we can more or less dismiss Guttman scaling for the time being, because we're going to look at Mokken scaling. And Mokken scaling was developed by Robert Mokken, who was born in 1929 and is still alive. And Mokken suggested only that for non-parametric item response theory, he didn't call it Mokken scaling, it was named after him, he said that item characteristic curves only had to be monotone and non-intersecting for a scale to exist. In other words, the precise shape of the item characteristic curve didn't really matter. They just had to be increasing with the latent trait across the whole of the latent trait. That means monotone homogeneity, and they didn't have to cross over or intersect. So this is what an item characteristic curve looks like in item response theory. This item characteristic curve is somewhat idealized and S-shaped, and in parametric methods like Rasch modeling, they are indeed S-shaped, and the extent to which they conform to that shape is part of the analysis. However, in Mokken scaling, it's only conventional to represent them like this. They don't have to take that shape. As I say, all they have to do is to be monotonely homogeneous and non-intersecting. And again, on the x-axis, theta represents the latent variable. And essentially, an item characteristic curve is a probability density function. It's a measure of the likelihood or the probability of a score being obtained on an item as the latent trait increases. So let's have a look at two item characteristic curves. If you have two item characteristic curves, they're positioned at different points on the latent trait. While these don't intersect, you can see that they're quite different from the Guttman item characteristic curves. They cover broader ranges of the latent trait. And item 2, because it's further along the latent trait, is described as being more difficult than item 1. It represents more of the latent variable, and more difficult items will tend to have lower mean scores on the latent variable. This item shows monotone homogeneity. In other words, across the latent trait, the item characteristic curve continually increases. That's all that monotone homogeneity means. This item violates monotone homogeneity, and you can well imagine that if an item does this, it's no use because you can't interpret the score on the item. These items are dichotomous items. They're doubly monotonous. In other words, they don't intersect. You've seen that example already. Difficult to really visualize and explain double monotonicity, but here's another car wash from Taiwan, and if you look at the score top left, which is 100 Taiwan dollars for the car wash, and you go down the way, it increases to 200 for whatever the car wash is. I can't interpret the Chinese writing. And if you go along the top from 100 to 150 up to 5,000 Taiwanese dollars, it constantly increases. In fact, if you go from that point in any direction on that particular table there, the values increase, and that's an example of double monotonicity. The values don't intersect at any point. If these were scores on a latent trait, then they would look like that if they intersected. And again, I think you'll agree that if items intersect, then you can't interpret them properly. Beyond the point of intersection, you can't relate the score on the latent trait to the score on the item accurately, because you actually don't know which item is being scored. Let's just quickly look at dichotomous compared with polytomous items. The previous assumptions all hold for dichotomous items, where the item response function, or the item characteristic curve, is equivalent to the item step response function. I've called it item response function because I'm relating it here to what's called the item step response function. But don't forget that the item response function, the IRF, is the same as the item characteristic curve. So what's an item step response function? Well, an item step response function is the change in the latent variable between two steps in a Polytomous scale, for example between disagree and strongly disagree. So let's take a look at item step response functions. In the top graph you've got two sets of item step response functions. The dotted lines are for one item and the continuous lines are for another. And these are the item step response functions for a 4-option question. I'm sure you'll appreciate if you've got 4 options in a question, say 1, 2, 3 and 4, you've got 3 steps between them. And something to note here is that the item step response functions for 2 different items can intersect, but the item step response functions for one item don't intersect. If they did intersect, they would violate double monotonicity, and those items would be. And here we see 2 sets of item step response functions, and below them their respective item response functions or item characteristic curves. And what you see top left are 2 sets of item characteristic curves which don't intersect with each other. In other words, they are definitely doubly monotonous, however they intersect with each other in such a way that the item response functions down at the bottom do intersect. On the top right you've got 2 sets of item step response functions. Again, they don't intersect with each other, and they don't intersect with the other item step response functions, and the item response function at the bottom doesn't intersect. The message here is that you cannot interpret whether items are going to be doubly monotonous or have invariant item ordering if they're polytomous, and we'll come to that in just a minute, just because the item step response functions are non-intersecting. So, next we look at double monotonicity and invariant item ordering. Well, for dichotomous scales, double monotonicity is kind of the equivalent of invariant item ordering. It isn't exactly the same. For invariant item ordering, you have to have a very special property indeed. And the definition of invariant item ordering is that item ordering is the same for all respondents at all levels of the latent trait. But invariant item ordering is really something that's only recently been studied in polytomous items. And here we see an example of invariant item ordering of polytomous items. It looks very like double monotonicity, doesn't it? And it is really the equivalent of that for polytomous items. However, strictly speaking, this would only show invariant item ordering if both of these items were ordered in exactly the same way at all levels of the latent trait and for every individual who responded to the item, and that they didn't do this, that they didn't intersect at any point. So that's a violation of invariant item ordering. Again, it looks very like a violation of double monotonicity. I've used the same slides to make the same point. So, while invariant item ordering means that item ordering is the same for all respondents at all levels of the latent trait, double monotonicity in polytomous scales does not necessarily mean invariant item ordering. Double monotonicity refers only to the item step response functions and not to the item characteristic curves. So here we've got another example here of item step response functions that are not intersecting at the top. They show double monotonicity, but in fact the item response functions or item characteristic curves intersect, and they don't show invariant item ordering. So the criteria for a Mokken scale, there are various parameters which we're not going to go into in any detail in this session. I just want to run them past you literally. Scalability, the items need to be scalable, and the minimum value of scalability, or H, is greater than 0.3, And scalability is actually a measure of the number of Guttman errors in the scale. In other words, the number of times items are scored in the wrong direction relative to one another. Reliability, or ρ, should be greater than 0.7. This is a single sample test-retest method. You can describe it as being analogous to Cronbach's alpha, although it is different and considered to be superior. We can also calculate the probability of obtaining a Mokken scale using a Bonferroni correction because there are multiple iterations. We should have low violations of monotone homogeneity and of course double monotonicity, and it's desirable to have invariant item ordering, although I must make it clear that that is not an essential feature of a Mokken scale, and this is gauged by looking at the items and also by measuring ht or ht-trans, which should be greater than 0.3, and that's a measure of the distance between the items. The greater the distance between the items, the greater the accuracy, or the precision as some people describe it, of invariant item ordering is. But invariant item ordering can only be verified by plotting the items and looking at them. So here are the ranges of h and ht. 0.3 to 0.4 indicates weak scaling or weak invariant item ordering. 0.4 to 0.5 indicates moderate scaling or moderate invariant item ordering, and then greater than 0.5 indicates strong scaling or strong invariant item ordering. So let's compare factor analysis with Mokken scale. For this I'm going to use one of my own scales, the Edinburgh Feeding Evaluation in dimension. This has got 10 items, and if you factor analyse it, the items look like this. You get 3 different factors. Up at the top right, one about the nursing actions. At the left, the indicators of feeding difficulty. But the one that's of most interest are the 6 items at the bottom, which indicate behavioural aspects of feeding difficulty. So the EdFed scale has these items scored never, sometimes and often. I think we'll agree that if people score never for all the items, the score is 0, and we know exactly which items have been scored because there are no other possible combination. And likewise, if we have a score of 12, we know that all of the items have been scored positively at 2. So there's no dubiety there about which items have been scored. A score of 6 is obtained in various different ways with various different combinations. So this would be what would happen with classical test theory or factor analysis. You never quite know which items are contributing to the score, the final score on the scale. So the EdFed forms a Mokken scale, and there have been several studies to verify this, and there's a hierarchy of items from general refusal to eat up to leaving the mouth open. Don't concern yourself too much with the details here at the moment. This has been verified in other samples in the UK and in Taiwan. So let's watch the scale score here as the item scores change. If a scale forms a Mokken scale, then you can only have certain scores or very limited ranges of scores from certain combinations of items. A score of 1 would be scored like that, a score of 2 like 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's the pattern of scoring that you would see. There is some leeway within that for slightly different scores, but that's the general pattern. There's a hierarchy of scoring between the minimum and the maximum score. So that's just a quick demonstration of the value of item response theory over classical test theory. You know from the total score on the scale which items have been scored. So here's just some examples from my recent the General Health Questionnaire 30. Mokken scaled that. It's got several dimensions. However, what we've found is that there's a hierarchy that crosses these dimensions from simply being unable to face up to problems generally through to feeling that life isn't worth living. So it's anchored at a very severe end of feeling suicidal at one end of the scale. this is quite common that these sort of scales are anchored at the extreme end. But there's a very sensible and consistent hierarchy in between those two extremes. For the clinical outcomes and routine evaluation outcome measure, or the core O4 items, we found that 6 or 7 of these Mokken scaled, and again the increasing level of difficulty went from I've achieved all the things I wanted to do, which is actually negatively scored, through to having made plans to end my life. Again, you see this familiar extremes at the end of the scales, and a sensible hierarchy of items in between. The personal disturbance scale, again measuring psychological morbidity, and again a similar pattern here, increasing level of difficulty from being so low on spirits that they've sat for ages doing absolutely nothing, through to being so depressed that they thought of doing away with themselves, with again a sensible hierarchy of items in between. And finally, on the examples, the voice symptom scale. This is a measure of voice problems in people who've got a disorder called dysphonia. And this scale has an increasing level of difficulty from simply having a hoarse voice through to social isolation. And if you look at the items carefully, as you go from bottom to top and the increasing level of difficulty, you move through somatic symptoms, through problems actually drawing attention to yourself, feeling stressed and nervous, up to social isolation as a result of this problem. So that's the usefulness of Mokken scaling. It arranges items in an order based on their mean value, but only selects the items that meet certain stringent criteria. So finally, some developing issues in Mokken scaling. Well, one of these is that large values of ich trans, which is a measure of the accuracy of invariant item ordering, don't guarantee that items do have different intensities or are actually showing invariant item ordering. An example of that is this very high HT here, and that's being caused by that single item that's lying far away from the rest. And that's observed in several subscales of this personality scale. So you have to be very careful to make sure that there aren't items which could be described as outliers lying far from the cluster that are artificially increasing the size of HT, or the measure of the strength of invariant item ordering. Strictly speaking, when you see that kind of thing, you should remove that item and see if the remaining items still show invariant item ordering and a reasonable strength of accuracy. It's possible now to calculate standard errors and confidence intervals for scalability coefficients and to compare them on that basis. And the HIJ, this is the 95% confidence intervals for the item pairs, should not include 0. In fact, what it means is it should always be above 0. And the 95% confidence intervals for individual items and for Mokken scales should not include 0.3, which is the minimum value for a scale. There's also work by Strat, which is trying to investigate, using simulated samples, the sample size requirements for Mokken scaling analysis. And this table, which is quite hard to interpret very quickly if you're not familiar with it, looks at mediocre, adequate, good and excellent per element accuracy. That means the ability to allocate items to a scale at different levels of item scalability and different levels of correlation between the scales. So it gives you some idea, but from simulation, of what the likely sample sizes are if you know these other parameters. There's very little work and none related to using these parameters on real data as yet. And finally, a paper by Smits, Timmerman and Rob Mayer, who's one of the experts in Mokken scaling, who's investigated the concept of unidimensionality and wondered really what it means. And despite their expertise in Mokken scaling, they've actually asked if Mokken scaling is not so much a type of item response theory, but a type of latent class analysis that may be classifying people and not items, because item response theory actually does both. But Mokken scaling may be more dependent on the clusters between people than on the scores on the items. However, these are at what I would call the outer limits of Mokken scaling. These are new developments and not things that we need to worry about too much at the moment, and in fact it doesn't really matter how Mokken scaling works. The fact is it works, and there are parameters there whereby you can judge the quality of items and the quality of the scales. So the conclusions and prospects, well, Mokken scaling is useful and remains very useful. It's being developed all the time. We must treat strong scales with caution and dig deeper, look at the items and don't just interpret the strength of the scale naively. We can now calculate standard errors and confidence intervals for scale coefficients for individual items pairs and for the total scale, and this could prove to be very useful. It hasn't been used very much at the time of doing this presentation, but I'm sure it will prove very useful in the future. And we can now estimate sample size, but we need to be doing this on real samples to see how it works in the real world. And there are, it appears, some issues about unidimensionality and exactly how Mokken scaling is working and what it means. For a non-technical introduction to Mokken scaling, this paper from the Journal of Clinical Nursing, first authored by myself along with Van der Ark and Rob Mayer, who are experts in Mokken scaling, and other colleagues who've worked with me using Mokken scaling. This is a very good non-technical introduction to Mokken scaling, and I would strongly urge you to read it. If you want to look at some of the examples of my work from the past, then these papers here demonstrate some of the scales that I've already talked about in this presentation, but some other ones are included there as well, and it'll just show you how Mokken scaling has been applied and has been shown to be useful and to give useful insights into different scales. Finally, that's my email address. You can email me with any questions or comments. That's my ORCID number if you want to check my publication record, and also you can follow me on Twitter. Thank you very much for listening.